But now let's use our Lorentz transformation to arrive at some more concrete expressions for how we deal with this time dilation. So, to start seeing the effects of time dilation, we're going to need to introduce two observers. So we're going to have an observer A that defines the frame X and CT, and then we're going to consider another observer that moves within this frame. And now, just for simplicity, I'm going to consider an observer that moves with a constant velocity. So that'll be the observer B. So the observer B moves through the A frame, but they themselves define their own reference frame, which I'm going to call X hat and CT hat. And now, of course, we can Lorentz transform between these two observers. B is moving with some relative velocity through the A frame, so we can just use a Lorentz boost to transform between the CT and T hat coordinates. So if I just write now that the moving observer's coordinates, C, T hat and X hat, are simply going to be given by our Lorentz boost in the X direction as a matrix acting on the stationary A-frame coordinates. So this is the observer B, this is the observer A. So hopefully this is all familiar, but we're going to now use this to derive or to see the effect of time dilation in action. And so to simplify things, what I'm now going to do is, first of all, realise both of these observers are passing through the origin of the A frame, and I'm going to cleverly synchronise the clocks so that at this origin point, at the point T and X are equal to 0, I'm going to also say that the coordinate T hat and X hat are 0. That's just going to keep things easy to deal with. So now what I want to do is I want to consider a fixed interval of time in one of these frames. So let's say take the A frame, measure an interval of proper time, and then let's Lorentz transform and see what happens to this interval. And so now a nice way that I can do this is if well, first of all, we've realised we've synchronised our origins, and so I can now effectively represent an interval of time in the A frame, or just an interval of proper time in the A frame. I can just now represent effectively by a vector that just points along the time axis and has the length of the interval. So I can say that a delta of proper time in the A frame is just now measuring the time interval from the origin. I can just say that the interval is just the coordinate CT wherever we are on this axis. So our interval of proper time is just going to be now expressed as a point in our A frame, or rather just a point on the CT axis. And so we're just going to see it's just given by the coordinate CT. And now what I could do, maybe to make this a bit clearer, is rename in the A frame the T coordinate just to be tau, and we're going to call that our proper time. And then we're going to see what happens to this proper time as we move into the B frame. So just so you're absolutely clear what I mean by this, I'm looking at the coordinates of a point in the A frame, a point that just simply lies on the tau axis, and then I'm stating or just assigning to this point, I'm saying that the value of the interval from the origin to that point, the value of proper time, is just going to be the value of that point, because it's just measured along a single axis. And so this is what we're going to work with. Effectively, we can now realise this, well, it is representing a point in our A frame, it's representing this point, but we can now just equally think of that point as the vector, which just points to that point effectively. So it has a t component of c tau and then 0 space component. And now we can just use our Lorentz transformation to transform this vector, or just work out what the coordinates of the transformed point are going to be in the moving reference frame. So to do that, we just need to remember the form of our Lorentz boost, which was the following, but our new coordinates, and then the Lorentz boost matrix, which we derived previously, which then linearly multiplies our old coordinates, which are now the tau and x coordinates. And so this would be a general expression for working out the points of now any point in the B frame using the point in the A frame. And so we can look at our designated point, which is c tau, i.e. x is 0. And we can work out what the coordinates of this point are going to be now in our B frame. Just label the frames. So just simply multiplying out these matrices, we're going to find gamma c tau, and then minus gamma v tau. So what this thing is it's specifying essentially now a vector in the B frame that is going to be pointing to the point in the B frame that corresponds to the point in the A frame after it's been Lorentz transformed. And so now, just an aside quickly, if we look at this expression, we can maybe recognize something. If we just ignore this tau, this looks an awful lot like the full velocity, and now it really is a full velocity if we simply were to just take the tau derivative of this vector. Essentially this vector is just specifying a position in Minkowski space, or just the coordinates of a point. And if we think of now letting this tau parameter vary, this is going to trace out some world line of points, and then just taking the derivative with respect to the tau parameter is basically just going to remove it since it's a linear parameter, and we just effectively now arrive at the full velocity vector. But let's keep it in terms of a position vector for now, and we're realizing that this vector is now pointing to the position of this original point A, but now in the frame B. And so we can immediately see we've gone from a completely vertical or time-like vector with no spatial component. We now do have some spatial component. We can understand the fact that we have to have a negative here if we just first of all realize from this diagram, essentially this observer B is moving away from the origin of our A frame, and so from the perspective of B now, remember that this is now describing the positions of this point from the perspective of B. From B's perspective, it's going to see that point now travelling in the opposite direction because B is moving in this direction. So that's where the negative comes from. Don't let that confuse you. Okay, so now we have everything that we need. Essentially, we can now just compare these two expressions and we can see what's happened to our vector. Well, we don't really need to consider the space component. It has changed, but we're not interested in the space. We're just looking at how the interval of proper time is going to correspond to an interval of coordinate time. And so just now simply comparing these two values, we see that the proper time interval A, which was, or had a length of c tau, has now become the coordinate time interval delta t hat in the B frame, and it has a length given by this value here, because remember we were conveniently setting our origins to be in the same place, and so we can just directly read off the value of this coordinate time interval as simply now just gamma c tau. Okay, so what we've now essentially realised, or arrived at is just now really a restatement of what we had originally. We've now derived that a length of proper time, how it is Lorentz transformed into another frame, it's essentially just going to pick up a factor of gamma. Because if we just now consider just a ratio, this ratio of our coordinate time, how it compares to our proper time, just divide this by this, and we're simply just going to find that it gives us this Lorentz factor, gamma. And so this is now really how we can understand this gamma factor in terms of our now time dilation. We can see here that we know that gamma as a function is just this thing which starts at 1 and then increases up to infinity as we approach v equals c. So this was the Lorentz factor. And so now as we stay relatively low velocities, delta tau and delta t are effectively the same thing because gamma is just 1. But now as this coordinate velocity starts to approach c, this gamma is becoming much, much larger than 1. So from this ratio we can just simply see that the coordinate time as measured by a stationary observer that sees you travelling close to the speed of, or close to this speed c, the coordinate time that that person is going to measure is going to be much, much larger than the proper time that you yourself would measure. So this now has the physical name, or the phenomena is referred to as time dilation, or sometimes you'll hear it stated as moving clocks run slow, but I don't really like that interpretation of the expression. It should really be saying that if you're stationary and you're watching a moving clock, then you're going to think that clock is ticking faster than it actually is. The statement should really say that stationary clocks run at the maximum possible speed, or they are the only proper measure of time. That's why we call this the proper time. And then any other observer that sees that clock moving is going to somehow think that that clock is ticking slower than it actually is. Or rather, they're going to associate a greater time interval than the actual smaller interval of time which the proper clock measured. And so you'll sometimes hear this time dilation referred to or stated by saying that moving clocks run slow. Now we can clearly see why this is the case. If you're now a stationary observer and you're watching some clock moving past you with some velocity, you're going to think that that clock, or that more time has elapsed from your perspective than actually elapsed as measured by the clock's perspective. And so you would think that the clock is running slower than it actually is, because you're going to be measuring that the time elapsed is actually much greater than really the clock has elapsed in its own frame. So in summary then, we've now formalised and formulated this physical effect of time dilation. We'd already started seeing it kind of fairly visually with just how these intervals are going to have to be distributed over time and space. But now using our Lorentz transformation formulae, we've been able to effectively arrive at a point we found in the first couple of videos, and we talked about forward velocity, but we now can have a really good interpretation for what this gamma is doing. Essentially, as gamma becomes much, much larger than 1, as our velocities approach this special value of c, it's now going to produce a much greater coordinate time interval than a proper time interval. And so if you're stationary and you see a clock moving past you very quickly, the time that you're going to think that that clock is measuring is actually going to be much, much greater than it is actually elapsing in that clock's rest frame. And so this has the name, or this is given the name, time dilation. And now we're going to see something very similar, but in some sense opposite. We're going to see that times dilate and now lengths contract for moving observers.